Now we are going to start with the F block elements. So as you all know that when we talk about the transition metals, there occur a third transition series and the fourth transition series in which the F orbital electrons, F orbital elements are present, which are actually present inner to the transition elements. That is why they are called as inner transition metals. So these are actually in the third transition series we see lanthanum, which is 57 atomic number. It is the first element of the third transition series, and this 57 is after that the F block filling of F orbital occur, because in this case 4F is 0 actually, but after that what we see that 4F the filling of 4F orbital take place starting from 1 to 14. So this is what is the lanthanide series, because you can say its preceding element is lanthanum. That is why it is called as lanthanoides or lanthanide series. So in lanthanoides, what we observe that there is a filling of 4F orbital, successive filling of 4F orbital starting with 4F1, 4F2, 4F3. Likewise, it can accommodate 14 electrons. And if we talk about the actinoids, then they are present in the you can say the fourth transition series starting from the actinium. That means the first member is actinium, in which there is no electron in the F orbital, because the F orbital is supposed to have greater energy, right, as compared to the S and the D1. So that is why the filling of 4F occurred later in this case. But followed by actinium, there are actinoids starting from the thorium, that is with 90 atomic number, extend up to lawrencium, that is the 103 atomic number. In it, successive filling of 5F orbital occurred, that is starting from 5F1 extending to 5F14. Right. So this is what is the lanthanides and actinoids. I think it's clear that lanthanides and actinoids are inner transition metals, and why they are called so? Because they are present in inner to the transition elements, that is the after lanthanum and after actinium in the third and the fourth transition series. In this, the filling of 4F orbital take place, in it the filling of 5F orbital take place. And if we talk about their general electronic configuration, it is going to be somehow like this. That is n-2F ranging from 1 to 14, that is the anti-penultimate shell, followed by the filling of penultimate shell, and then the valence shell, or you can say the outer shell, the final shell. So it is n-2F ranging from 1 to 14, n-1 the 0 to 1, and ns obviously is going to possess 2 electrons. So if we talk about the lanthanides, in this the filling of 4F orbital will take place. So this anti-penultimate will be 4F, penultimate will be 5D, and the final shell will be 6S. And the electrons remain same, 1 to 14, 0 to 1 and 2. And in actinoids, there is a filling of 5F orbital. So anti-penultimate is 5F, penultimate is 6D, and the final one is the 7S. The same electrons were ranging from 1 to 14 in anti-penultimate, 0 to 1 in penultimate, and ns2 in the final shell, that is the 7s2. So this is what is the electronic configuration. Now coming on to their oxidation state, we know that that the number of electrons that actually participate in bond formation determines the oxidation state. So we see here that the oxidation state, which they mainly show the lanthanides, it is +3, but sometimes they also show +2 and +4, and where they show actually +2 and +4, where you can say that after the removal of 2 or 4 electrons they are going to gain stability. Like you can say that some achieve noble gas configuration, in some cases they are half filled, imparting the stability, some becomes fully filled, so imparting again the stability. So whenever you encounter these 3 cases, at that moment you are going to see an anomalous you can say the release of the exceptional release of electrons, because after doing that they somehow attain a stability in some of the manner, either in the noble gas configuration, or they are half filled, or they are fully filled. Examples I have already mentioned here. So now if we talk about their oxidation state, their dominant oxidation state is +3. But we can also see +4 here. Again the same reasons, because see, whenever you are talking about oxidation state, so for any other element, for any element actually, if there occur an extra stability due to noble gas, half filled orbitals or the fully filled orbitals, there you need to take an exceptional case. So whenever you are writing an oxidation state, or you are taking into account the oxidation state of the elements, just keep these points in mind. And you know that whenever we talk about the oxidation state for the actinides, it increase up to the middle, and after that it just decrease because due to the filling of the orbital, and moreover we know that after that somehow the size actually decrease and the nuclear charge increase. This is what is the lanthanoid contraction, or you can say in this case it is actinoid contraction. The factor is same. So, what is lanthanide contraction? Why we see that the oxidation state increases up to middle and after that it starts decreasing? What is the reason behind? So, the reason is with increase in atomic number, what we see that the size actually decrease. Otherwise, the opposite should happen, but here when the atomic number is increasing, the size is decreasing, because as we move more and more, the f orbitals electrons are increasing actually, and we know that f orbital has a diffuse shape and it actually show a poor shielding effect. So, it cannot shield its valence shell electrons in a proper manner. So, that means it won't prevent the outer shell electrons from the nuclear charge, and that means the nuclear charge is somehow reaching the outer shell electrons. They are pulling more effectively, and that is why leads to shrinkage in the size and increase in the ionization energy. So, that is the reason we see that the oxidation state start decreasing after the after the middle, because there when there is an increase in the inner shell electrons, the shielding effect is again going to be poor, and poor means more attraction for the valence shell electrons. More attraction means shrinkage of size, and that leads to the increase in the ionization energy. So, in the similar way you are going to answer for the lanthanide contraction, and similar you are going to do it for the actinoid. What is going to change? The change is that here we are going to concentrate, you will be writing that the progressive filling of 4f orbital, and for this you will be writing progressive filling of 5f orbital, because they both differ in the filling of the 4f and the 5f, that's just. So, you need to mention that, otherwise the basic factor is same, that with increase in the atomic number the size is decreasing, because as more and more electrons enter into the f orbital, so due to its diffuse shape, poor shielding effect, the shrinkage occurs, and due to which the ionization energy increase, and that is why we see that oxidation state actually decrease from the middle, right. So, this is what is the oxidation states for the lanthanides and the actinoids.